hello everybody. We're doing a little bit of an unconventional stream today. I got a big test tomorrow, but the thing is, Sparking Zero comes out in 30 minutes. So, while we wait, on stream, what I'm going to do is I'm going to be teaching you guys my course, what I'm doing, because supposedly teaching is one of the best ways of learning. Alright, let's pull up. Yeah, how is everyone doing today? I am doing okay. I've been just studying for this, quiz thing, test thing. So what we'll be teaching about is time complexities, alright? So, I mean, I might be jumping into this a little bit quickly. So this is a computer science course teaching you the efficiencies of, like, how to be more efficient with your code. Alright? I am doing this completely on the fly. I did no preparation for this. All I did was just, oh, okay, I'll just open up my notes, my school notes, and just try teaching from there, right? I have my drawing tablet. I don't even know where my drawing glove is, now that I'm thinking about it. It's actually... Yeah, it's somewhere, but I don't got it. So we'll be teaching about algorithms and time complexity. So let me pull up a simple code. Okay. Because I cannot code while this is, like, on this, right? Okay, let me look up a simple... You know what? Yeah, whatever this is. I'm just gonna steal this. Oh, okay. Probably should just copy and paste it, but sure. So, here we go. I'm using a Microsoft Paint to be able to teach this. So we start with this. So, typical code. I think this is, what is this? Java? I think this is Java. Printf? No, not Java. Trying to think. What uses printf? Python. That's what. No. Oh, C. Oh, that's why I got confused. Yeah, I've done all, like, 3 of them, so I'm like, it's one of them. So we start here. It's like, the idea of this is, let me just get a... Oh, I don't have it set to, like, be able to do undos. Okay, great, lovely. I'll just use the keys then. So basically, what we're trying to figure out is how fast is this code, alright? So we start off, something simple, like, let's say right here, let me just, something simple like this. Oh. Let me change it to a better color, like a red. So this is a simple program, right? And, okay. I'm a little bit, like, trying to think of, like, how far do I have to assume to get you guys at this point? So it's like, okay, I guess I'll just start from the beginning. So, main is the main function of a piece of code. So it'd be like how you start it, like, oh, everything branches off of main, alright? This is a for loop, where it's like, for everything until this, do this. Oh, wait, no. For this, until this, you do this. Alright? So from there, we go, and this is just like to increment it, to move it like forward or backwards or whatnot. Alright? So to explain this would be from in main. Oh yeah, okay, I guess int is a, actually no, that's just not. Int is a integer, which is a solid, it's basically a base number That's really all you need to know. for this at least. So for every int, and then this is a variable that tells you like that stores the information of what it is. All right, so I think that's enough. So for every integer variable I, it starts at 1, and the loop goes into as long as I is less than or equal to 10, because this is like a less than, and that's an equal sign, so less than or equal to 10. And every time it repeats I++, which means it's effectively like every time it does it, it's I plus 1. Okay? So it's basically I plus 1. So now we got this somewhat situated. It's time to explain what is time complexities. All right. So time complexity. Well, okay, yeah, we just basically explained what an algorithm is. So to explain, now we're explaining kind of time complexities. So if you do computer science, you'll learn about this thing called big O notation type stuff. So effectively, big O is the explanation of how fast does this program run, okay? So if the program is just like, let's say, since we already know what I is a variable. If I equals 1, okay? How fast does it get through this? So in this case, something like I equals 1 has a time complexity of O1, okay? Because it's only one operation, and that's it. So, and then for here, a for loop, typically, you have to look at whatever, it's like, okay, how's it doing here, and how much does it increment, alright? So, for this for loop, if you look, so generally it's a good idea to start from, like, about all the way at the furthest point. So here, so printf d/n, okay. So what this is like, printf is print function. It tells you to print it onto the screen, whatever you have in here, okay? The quotations is what you actually put in. This part is basically telling you to grab the variable, okay? The variable being, you do comma, and then whatever this is. So variable I, which comes from here, is printed here. This is basically teaching you how to move to the next line. So it'd be like, okay, so let me just do this for you. So for int starts at 1. Okay, if int is, this is this function is a modular. I think it's called modulus. I don't actually fully remember, but it's basically like, if this divided by 2 has it, if it's like, it's like the idea of like remainders when you're doing division. So if this modulus 2 equals 0, so let's say it's a 1, the modulus of 2 would be 1. Okay, so 1, 2 would equal, oh crap, you don't actually see that. Okay, right, because I cramp a lot of things inside, so I don't accidentally dox myself a bunch. 1 modulus 2 equals 1. Because it'd be like 1 divided by 2. Well, you can't exactly divide it by 2. Okay, in this case, because it's whole numbers, you can't divide it by 2. So the remainder of that item, of that number, is 1. So the remainder of 1 divided by 1 modulus 2 is 1. Okay? Yeah, let me just try fixing going through whatever I have. Okay. Oh, yo, is that C? Yes, it is. Oh, I'm actually surprised. I thought I had something. Oh, I'm sorry if you left, but I thought I had my. Oh, okay. I guess I have to work with that. Oh, that's my bad. I thought I had a thing open that was supposed to show thing messages, but it just didn't. So I'm sorry, I didn't miss. Strav. Yeah, this is C, but I'm using C as an example to teach this. Okay, right now. Oh, wait a minute. Oh, I thought this changed it. Okay, just give me a moment. I need to change the game category. Get that out of here. Just chatting. This is just chatting. I have like 15 tabs open. All right, so whoops. So yeah, we're here modulus. So we read from here. Okay, if I is divided by 2. Okay, so basically, trying to think of how do I do this. Okay, so the first function starts at 1, checks nothing, so blank. Okay, goes to the next one. Now it's int equals 2. Int is now 2. Okay, so 2 modulus. Let me actually check if it's actually called modulus, because I don't want to like be spewing some misinformation. C. Modulo or yeah, it is modulus. It's basically asking for a remainder. Yeah, modulus 2 equals 0 because 2 basically divided by 2 is 0. Like, there's no remainders. So it would print 2. Okay, so the next one moves next to 3. 3 modulus 2 equals 1 because there's still a remainder. So it'd be blank. And then 4 would be the same thing. 4. Okay, I just gotta see. 4 modulus 2 would equal 0 because 2. It's like kind of like. It's like repeatedly hitting it with like. It's like dividing it. Yeah, right. So 2 goes into 4 2 times. So it's just 0. No remainders. And 5 has a modulus, so no. And 6, 7, no. 8, no. There's no 9, and then 10. So, overall, it did 10... I don't know. Oh, just 10 commands. 10 commands, alright? So we start... so we got 10 of them, alright? And then we check here is also like I equals less than or equal to 10. So in this situation, we see this. Okay, this is this function is O to the 1 because it's just a single operation, alright? And then we move out of this. So the for loop, since the for loop goes all the way to 10, it's technically O of, well, really 10. But if you actually like, if it was more like, let's say, typical computer science variables, we use n as the variable. So if it's like, you would write it like this, like n. So then that'd mean the, can you see that now? Yeah, you can. So it'd mean the for loop is O to the n. I mean, really, this is at when it was 10, it was actually n2, but like, I'm trying to like simplify this. So it goes to O to the n because you have to go through the loop n amount of times. All right. Okay. Let me just erase everything. How do I up the size of this? Oh, I guess I can just grab this and just vaporize it. Alright. Let me just grab another thing. Okay, Control C, Control V. There's something wrong here. Oh. Yeah, that didn't dox me or anything. Is someone adding me right now? Someone telling me something on Discord? I don't know how to use this fangled old thing. Like, why can't I paste no more? There's something I'm missing here. Alright, I guess I'll check on my phone just in case so I don't accidentally show too much. Ooh. So, okay, from there, now I've explained partially what time complexities are. Announcements. Oh, no. Nothing important. Okay, Maybe I should have done this in my art drawing program, you know? Let me actually go and let me go do that actually. Oh, now it shows up. Okay, it just took a long time. Lovely. Oh, blank. Let me just pull up my preferred art thing of choice, being fire alpaca. Let me just that's fine. Is it showing anything? No. Alright, we're going back to... We're starting with this, and then going... Oh, it's in, Let me just make a white canvas, so we can just change the layers. Algorithm time complexities. Let's do it to 30. Okay, 30's too big. 24. Nope. 14. That's fine. Okay. Alright, now... Where do we go from here? Let me just get my notes again. Oh wait, I can just probably... Nope. Copy. Oh, okay, it just doesn't want to... Okay, I guess I'll have to do like a screenshot type thing. I wonder how much you see when I do this, actually. Like, do you see the blank parts? Alright. So, we teach something, time complexities. So, let me go explain everything here. Oh, we've still got, like, about 10 minutes before it comes out. Okay, so, constant is constant time, right? So, it's nothing, it's generally, like, a type of modifier towards everything else. So, it's like, oh... Whatever, it's like, if the function is strange delay on my my pen, hey? Maybe I can't work with this. Is it probably stabilizers? No. Who knows? Who knows why it's like taking an extra second. But basically if it's like, oh, okay, I guess I'm just using my mouse now. Okay, let's say it's 2n. O of 2n, okay? So the idea of O of 2n is that 2 would be the constant. It does not change. That's really it. That's not, it's just like a modifier. It's effectively like a modifier for it. Let's see. I'm just gonna quickly check if Sparking Zero, you can download it. They just don't want to let you pre-download this game, huh? That's stupid. It's like a 30 gigabyte game and they don't want you to download it. Oh. Guess one of my lights went off. Turned it back on. So typically with constant time, it generally doesn't matter how you do it. You can just usually you reduce it down from 2n to just O of n, because the constant times are generally, you can just like ignore it because it doesn't make a huge difference in the long run when it comes to time complexities. So log n. Effectively, log n is if you were how would you say it? I never really liked using logs, but effectively log n is moving. Let me get rid of these. Also go into a new layer. So log n. Okay, let me try thinking. How do I explain log n? Typically log n is more actually like a log 2n, and then, you know, from there we just explain it. Oh, let me get a different picture actually. There's a different picture I could use that explains things in the background too. Time complexities. Yeah, this is pretty so yeah, this is the whole, generally the whole idea of time complexities. It's to use to check how fast things are. So going at so input size is like how much n is, kind of. Not kind of, it is. So at O of 1, it's always at 1 operation. Like, you could say big O is almost like the word operation. So O of log n is basically log 2n, in where let's say if you had a set of numbers, so, you know, let's say you had a set of numbers, you know, 1 to 10, alright? So log n, like the 1 to 10 is the n part, okay? And then the log part is the part that takes everything out. So it's like, so log would get rid of half, then get rid of half, then get rid of half. So it's like, it's a log, it's exactly log 2n. It's not n over 2, because 2 over 2 is a constant, is technically constant. Log 2n is basically dividing it by 2 each time it does it. And then n is the basically the total, like, a variable number. So, like, oh, you go through that list of 10. Yeah, I can just get rid of that. You go through the list of 10 here. So 10 would be n, because you're going, like, checking each individual thing. Alright? And log n is basically like how do I explain n log n? N log n comes from I guess I should explain each piece here. Constant time binary search is a searching algorithm used to search. Binary as in, how binary is zeros or ones. So it's like left, but in this case it's more closer to like left or right. Is it on the left side or is it on the right side? Oh, it's on the left side. We get rid of the right side and then we go from left, cut that in the middle again, cut that in the middle again. Alright? And okay, find max is basically just like, oh, we start at 1 and compare. A is 2 bigger than 1? Yes, it is. Now 2 is the biggest number. Is 2 bigger than 3? Yes, it is. Now we go back. But the point of like it being n is because you don't actually know. You can't solve it without without checking every single one, because sometimes you could just be lucky and it's like, oh, 10, and then it's 1 2 3 4 5 6 7 8 9. Oh, 10 was at the beginning. Technically, it could have been in 01 because you just checked the first one. It's like, oh, but the system doesn't know that, and you technically shouldn't know that. You only know that because you technically have access to the rest of the numbers to check, which is n. And log n comes from sorting. Like is a generic case for. Okay, let me try and explain how it is. It says sorting because typically the most efficient sorting algorithm is in n log n. Okay? I mean, technically it's actually n log n plus n. But the thing is, in that case, n log n dominates over n. So you can just get rid of that. So it just becomes n log n. But it's n log n because trying to think. Okay, how do I show this with just in a simple way? Probably just gonna just leave it. I explain. Okay, insertion sort is a. Oh yeah, my yapping song. Okay, we can get rid of these. Let me pull up an example for n squared. And so basically, if you do a nested array, okay? So, I probably shouldn't have gotten rid of it now I'm thinking about it, but 9, 10. Alright. So we have this. Then we have. Actually, let me just, actually. Just duplicate that. And is there a way to rotate this? Hmm. $90. Okay, so basically, like, something like this, okay? So, in this case, we'll set this variable to I, and this one to J. So, the idea of it is, we have to scan I of 1, j of 1, I of 2, j of 1, I of 3, j of 1, I of 4, j of 1 each time. So I is effectively an n. Like, if you just, like, stop adding these together, it's basically I times j to be able to search through all 100 numbers. Which, if you go from there, it's actually n times n. N as in the first one, and n as in the second one, which equals a time of n squared. And it keeps going on to, like, you know, if it has, so that comes from a thing called a nested for loop. Alright? So, so the thing I had before, let me go pull up a nested for loop for you. You know, I can get rid of that for now. Okay, so yeah, here. You can see a nested for loop. So there's an inner loop and an outer loop. So this loop is in time of n because of, like, you know, this. And this one also is in n. So n times n squared. This is the operation of 1. Okay. So from here, it moves on to... So this is a n squared type of operation. Not operation, time complexity. Okay, get rid of that. Let's move to the next one. What's the next one? Yeah, okay, no, this is the... N3 is basically the same thing, but in this case, it's talking about matrices, so it's like... How do I guess I'll get a picture of it. It's talking about the speed of matrix multiplication. So... This. So, let's say A is I, this is J, this is K. So from K of 1 equals A of 1 times B of 1 plus A of 2 times B of 4 times plus A of 3 times something like that. I think that's how it went. I don't actually 100%. I can't say it off the top of my head right now because I'm just like... It's a lot longer than I remember. Oh, it's a 15-minute song. That's why. Oh! It's already time. It should be time. I should be able to download the game now. Why is it... how do I reload Steam? I don't actually remember. How do you reload... Okay, okay, shut it down, and then open it back up, right? And then we still got... You still got me time for me to yap, because I gotta... I gotta download the game. Alright, time to download it. Put it in the C drive, because... It's a new game. It's probably got a lot of load time. Yeah, 26 gigs. Yahoo! Why do I have DLC? Huh. Alright, okay, So that's basically it. 2 of n. I don't even know. I mean, I didn't really even learn these two because it's like these are more like cases that's like it's not that important. Like you don't get to this. It's like, okay, is it a you don't get to this? No, you do. It's just like not really 100% sure how to explain this. But okay, we're done. We're done with these, so we just all right. Okay, what's the next part of this? Oh, limits. So typically, algorithms are done as let me just do f n equals. So typically, function they're like set like this. So it'd be like, I don't know, okay, that's a like it's effectively a function comparing like the algorithms. It's just a algorithm. Okay, and then I'll type in another one. G of n equals, let's just say n squared. I don't exactly have a way to abbreviate like that. So these are two things. So next we're going to be teaching about limits, which is basic, which teaches the way to actually compare how fast each function is, how fast they can grow. So kind of like the other one where it was like the chart where it's like where it shows different time complexities. This is what you use to check how fast it goes. So effectively, you put f of n over g of n, and then you check what it is, what the answer is when n approaches infinity. So it'd be effectively like, let's simplify this actually. F of n equals, let's say it just equals n, okay? Objectively, we know n squared is faster than n, okay? So what we do to compare limits is going from here, dividing them. What does it equal when it's approaching infinity? Basically, so like, if you wanted a bit of help with that, you could always just use like actual numbers. So you just go like, I don't know, like 100, okay? So what's 100 squared? That's like 10,000. Is that 10,000? Yeah, 100 times 100 is like 10,000. And then we go from, ooh, wow, someone followed on Twitch. Thank you, DaBaby _6EP. Oh, that's nice of you. I wonder if, I sure hope that my the things I put up for followers actually appears. I can't check that. I'll check that later. So from approaching 100, so it'd be like 100 to let's add 2 more zeros. Yeah. So effectively, the growth rate of this is effectively like that. So where this is n, 0, I don't know, something 100. So it's kind of like this. Not really. It's more like here and just. It doesn't actually start. It should be more like that. So it slowly approaches 0, which means it's this. Oh, I didn't even teach about the other stuff. I didn't. Oh man. Okay, so these symbols. So what I've been teaching was oh, it's because it's higher up in the pecking order, in the list. You know, I sure hope that the download isn't actually like affecting the streaming rates and whatnot. So this, let me just move this all the way to the top. So what we've been teaching was big O. Okay, this is little o. So little o is let me try to think of it. Okay, big O is like the function n grows slower than g. Okay, little o is function n grows really slow compared to g. So okay, let me see here. O how do I even like f of n grows, yeah, just like, yeah, big O f of n grows slower than g of n. Okay, little o is f of n grows significantly slower than g of n. This is something called big theta. Okay, so big theta means it's effectively if this was like also about n squared, so it'd be like 10,000 over 10,000. Wait, is it? Yeah. So it would equal about 1. If it was n squared over n squared, it'd equal 1. Or close enough to 1. So yeah, if f of n is theta to g of n, if it's not 0, we're basically looking at C here. It's not 0, and it's greater than 0 and less than infinity, which means this big theta grows at about the same rate, close enough to the same rate. You know, could be a little bit different depending on, like, you know, constants and whatnot. And then I think this is little theta, or okay, there's also one more called omega, and it has a variant called little omega. Oh wait, no, this is little omega. Omega, what's it? I think omega is kind of like the opposite of big O, where big O is like, oh, it's slower than, but not like insanely slow. This is, it's faster than, but not insanely faster than. This is insanely faster than. So f of this would be like if f was 3. So that would mean f of n is growing significantly faster than g of n, because c is approaching infinity. Yep, there's limits. Okay, what's the next subject I gotta teach about? Limit laws. Oh, jeez. Limit laws is basically algebra, more algebra, but with limits. Okay, let me just... Okay, basic limit laws. So assuming limit of f of x, for some reason we're using an x now instead of n, and the limit of g of x exists as x approaches c. This is why this stuff is always so confusing. They start changing the letters, and then it's like, it starts messing with my head. Let me just drink some water. You know, funny enough, yapping always makes me like super hungry. Like I don't understand what part of yapping makes me hungry, you know? Alright, what download speeds are we getting at? Actually, that's pretty hot. Yeah, this should be done. Oh, it says that it'll be done in like 30 minutes. Let me go get some food. And then while we're chatting, I'll be eating a little bit. Alright, I'm back. For a split second, I was like, oh man, what if I took a shot right now, you know? Celebration. Yeah, that's stupid. That'd be actually so stupid. I think someone has started streaming. So let me just, start that. Whoops. Wrong thing. Wrong thing to mute. Alright. So basically, what have I missed? This is basically like algebra. Typical algebra, so it's like limit times f of x plus g of x. What you can do there is multiply into it. Oh, whoops, my bad. Because I forgot to take it out. That, put a thing in. So what you can do here, because it's like a bracket inside of this, it's basically limit times f of x plus g of x. So what you can do is you can just multiply into here, and then multiply into here, which gives you limit of f of x plus g of x is equal to the exact same as if you did it inside, which is limit of f of x plus limit of g of x. Just like okay, the constant multiple law for any number k. For simplicity for you guys, k is what we were talking about as c. Okay. You know, I was thinking of like just keeping the mic on when I'm eating, but I forgot that my jaw does like a weird clicking noise. So it does like a clicking noise, so I feel like you would hear that. So it's basically, in this, it's like limit the limit times k times f of x. Technically, k does not have to sit in there, so you can just move it. So limit of k times f of x, it's k times the limit of f of x. It's nothing complicated. It's like you can straight up see like limit times this times that times this divided by that. You know, you just move it. It's nothing crazy. Okay, let me see here. Anything else? Limit law. Alright, for this one, we're talking about Master's Theorem. Weirdly, I had trouble with this until I actually, like, really sat down and read, like, what the hell it was actually saying. With Master's Theorem, it's basically like the function I was telling you about, I was using last time. So, what's it? F of n equals 2t of n over 2 plus, let's say, n. Here, we'll capitalize n. We'll have this both as, like, side examples, alright? So, Master's Theorem is the idea of, like, oh, we just pick out each number, you know, look at it separately to, like, see how it looks. So, in this case, in this example, f of n, actually no, 2t, 2 is a, okay, b is right here, so b, oh, whoops, b would be 2, also 2, and c isn't in here, but if it was, it'd be this, and c here is 1. You know, wait, no, not 1. It'd be the exponent if it had an exponent. Whoops. So if it had an exponent, wait, where'd it go? Oh, okay, yeah, I see what's up now. Okay, so it'd be like the exponent of this. So if it was n squared, that's c. C would be 2. But in this case, because there's nothing here, it's 1. Alright? So you plug that in, and it's like, you check. Oh, what was it? Is A, so in this case, 2. What does A compare to? B is 2. 2 of 1. Okay, let's check. A equals B of k, because 2 to the power of 1, wait, no, isn't 2 to the power, no, yeah, no, 2 to the power of 1 is 2. 2 to the power of 0 is 1. I mean, 2 to the power of 0 is 1, yeah. So then, we use this formula here. Which means this is n to the power 1 log n. This formula is n log n. Pretty simple. Alright, so from here, and then we can do other examples too. So it's like, let's say if it was just t, 1 being less than that, we'd follow the other thing. So it would be n of k, n, 1. That means this formula, that means this part overpowers this part. So it'd be like t n over 2. T n over 2. Yeah, whatever that is, that's less than whatever n, just n. So it would be n of 1. So let's say it was a 3 instead. Whoa. Did my model like mess it up because I'm just like jumping around? Nah, it's fine. Alright, so if it was 3, it'd become n log 2 of 3, which is like, what is n log 2 of 3? I don't know. I don't have my... So a good calculator down here? It's not here. So it's like you get the same thing with these two also. So that's Master's theorem. I weirdly had a lot of trouble with this. I think I'm just stupid. Okay, I guess we're gonna be talking. I feel like I'm missing a few slides because some of them are just like kind of. Oh, yeah. You just kind of know. This is like algorithms. Because I'm looking at my paper, my work, my notes. It's like I'm just not mentioning something called divide and conquer, which, I mean, technically we've already brought up because that's part of the time. I was already explaining it during time complexities. But probably should mention. I'll probably figure something out to like teach about that too. Oh, whoops. So substitution method is kind of it. Okay, it's not the master theorem, but it's a way to solve one of these equations. So typically, there are a couple ways you can do it. You can either do it by something called a recursion tree, substitution method, or master theorem. You would not usually use master theorem right at the beginning because I don't know. I guess it's just good practice. So I guess I'll go and explain both. Give me a second. Let me go cough. Okay. So with the substitution method, it's basically actually no, I can combine both substitution method and tree method, recursion tree. Tree sub. So the substitution method is basically okay. Jeez, talking too much. Is putting the formula of this back into itself to show a... Oh, jeez. To show a... what's it? A common, common something. Just like... Oh no, not a repeating pattern. So basically, you just put it in itself until there's a repeating pattern, and at the same time, I can show you through the tree. So from here, we can check. We check from here from n squared. Okay. So we start at n over 2. Okay. The 1's not important because it's a constant. It's because you know it's c. It's the constant. So from here, t of n squared equals 2t of n. Oh, you actually do see it. I just saw it in the corner of my eye. It's like you actually do see me when I do my screenshot. Plus 1. This looks awful. What is this? actually garbage. Okay. So, when you're doing recursion trees, this weirdly not instinctively. I did not think of this instinctively. So 2t is what you use to branch. That's how you know. So it starts 1 level, 2 level, 3 level. So this n2 multiplies into itself. So n over 2 times n over 2, which is n over 2 squared. Okay, and then it does another like branching. I'm not gonna show all the branches because I don't have space, and I'm not good enough using my mouse. And then it branches up. Oh wait, no, in here also. T of n. You know what? I'm gonna do this in text because t of n over 2. Wait, no, it'd be n over 4 now. N over 4 equals 2t. Wait, no, we got actually, it's 2 times 2, so 4t. 4t over n over 4 plus 1 plus 1. This is what it becomes. Okay? Which we see here is substitution right here. Is it 2? Oh, right, it is. Oh, I'm missing a part actually. It's 2 because it's it's 2 because it's this plus 1, which is where the 2 comes from. The 1 here comes from 2 because it's like, you see how it's outside on 2? So it's actually, it'd be more like you would move the 2 in here. So 2 times n over 2 is 1, which is where you get this whole formula, okay? And then if you just kept going down, you'd notice that it's like, okay, every increment is 2 to the power of 2, because it keeps multiplying itself by 2. And then n over 2 to the power of k comes from it, because you can see it goes 2 squared, it'd be 2 cubed, and more. So that's this thing. And 2 to k minus 1 plus moving down, that comes from the fact that these two are equal. If they weren't equal, you'd have to start dealing with like fractions and whatnot, which, yeah, I had to for school. Okay, let me go eat. So yeah, you figure that out. And at some point you can reduce it down because you can get rid of the constants. I don't know why 1 is there, actually. And then you end up with a 2n minus 1, which... I mean, technically this one's... What is this, like, log? So what? A is 2, B is 2, C is 0. So, what's it? A is greater than B over C. So that means... What's it? Let me pull up the master paper. N log 2 over 2. Oh, yeah, okay, yeah. Because it's 2n minus 1. 2 is a constant. 1 is also a constant. So which equals O of n. I realized that because it's like, oh, log 2 of 2. That's 1. So that means n of 1, which equals n. Duh. Still got 15 minutes. Okay, from here... Then you go look for the next part of it. That's theorem substitution. Okay, Huh. I guess I'll just, I move on to this. Oh, I already got rid of them. Okay, sure. How do I explain what else? Okay, divide and conquer. So the idea of it is something I've already explained earlier in the stream, where it's like, you know how binary search. So binary search of O log n, because the idea of it follows divide and conquer. So it's like, let me just... Yeah, I'm getting, like... Getting pretty tired now. I'm like, oh, I'm tuckering myself out now. So, the divide and conquer comes from the fact that it... Okay, we split it in half. Let's say we're looking for 2. Let's say we're looking for 2 here. So what we do is we'd split it in half. You know, either way, it doesn't matter. And we go, okay, oh. Okay. In this situation, it's already sorted and all that. But we start from here. So we start 1, 2, 3, 4, 5, 6, 7, 8, 9. If it was sorted, we'd have to actually add an n log n to sort this. But anyways, it's like, okay, the number we're looking for is 2. We don't exactly know where 2 is. Because, you know, we don't have perfect numbers like this. In a lot of cases, it'd be like 1, like 5 ones or something, you know? You can't just look, oh, number 2, that's 2. You know, it could also be 0. There could also be a 0 here, you know? You could also have a 0 here. And then all of a sudden your numbers are all wrong because they were manually put in to find it. So, like, let's say our number is 2. We look for this. Hey, is 2 here on the left or on the right side? Well, the number we're comparing it to is 4 here. 4 is bigger than 2. I mean, 4 is bigger than 2. But 4 is also... Wait, no, we don't actually do it like that. 2? We're looking for 2? Well, 4 is smaller than 5. Therefore, we cross this out, and we just lost half of the thing. And we don't need to search it because we know it's sorted, and we know it's not there. So then we go here, divide it in 2. Hey, we're looking for 2. Well, 2 is smaller than 3, but we're looking for 2. Therefore, 2 is on this side somewhere, so we can get rid of that. And then we do a final one, ignoring the 0. Ignore the 0. Alright. From here, 1 or 2? Is 1 2? Or is 2 2? Well, clearly, 2 is 2. Therefore, we get rid of that. Boom. So what we took an operation that would have taken 9 operations and turned it into 1, 2, 3. Which is immensely efficient. Like, okay, in this situation, because it's only 9, okay, that's not anything that crazy. But if it was like 100,000, instead of going through it 100,000 times, it'd be almost like square rooted. Yeah, man, let me actually like do it. Let me do it on my calculator. What's the answer to this? Okay. Yeah, that's not right. How do I do the advanced? I can't do advanced log. Okay, do I get it? Do I get the advanced calculator on here too? No. No, I can't. It'd be a lot, so it'd be like 1,000, 500, 250, 125, 60 something, 30, 15. You know, we'll figure this. Yeah, well, I'm just gonna hand wave that idea right now for the moment. I'm just gonna hand wave it. Anyways, that's what log n is, which is why we use Oh, yeah, video pause, yeah, continue. Wait, why is creative exercise still here? I thought I got rid of it. Huh. Because I remember I was like talking about how creative exercise has a copyright thing. Why is it back in this playlist? Alright, we're done. So that's basically divide and conquer. Is there anything like more advanced that I need to like specifically mention about it though? I'll look through my notes. Yeah, okay, it's just talking about sorting and how sorting is divide and conquer. And no, not really. Okay, let's move on to the next big one, closest pairs. Oh yeah, I love that. Okay, let me just okay, we start from here. So the idea of closest pairs is how do we search through all these points in a line, which is x, you know, we use an x and y coordinate, so x and y, we use an x and y coordinate. How do we find the closest pairs? Through, you know, distance formula and all that. Okay. Sure, we can do that. Okay. How about we do a for loop, okay? So for x equals 1. Okay, x plus plus, and then for y. Hey, look at that. Ain't that familiar? N squared. That takes n squared to go through all the points because we're going by first x and checking all the closest points. All of x and comparing the y's to it too. Is there a faster way? Of course there is. Do I know it exactly? Not really, but like that's why I'm trying to teach it. So the idea of divide and conquer with closest pairs is we split this in half. Okay, well, I guess we'll just do it at an angle. We just have those at the sides. How do you do this? Let me look through my notes and read them. Because this is one that was like, oh, this one kind of like bothers me. I'm like, oh, you know, I'm pretty sure I've talked about it. It's like, oh, the math started getting like complicated once I started like explaining, like trying to figure out other things. So okay. Oh, right. Yes. So, a simple way, not... This way isn't divide and conquer, but the easy way is you pick one of these and just sort them. You just sort one of these. Sort them. Which equals n log n, okay? But then, with the sorted ones, we can go through a list of n. List of n, which is y. A list of y. And just figure out which ones are the closest variables through that. Which is a plus n, and since it's plus, it's not n log n squared, it's... Because this is a constant, you cross that out, n log n. But, the idea of doing it for divide and conquer is a little different. Which is the one I was using the picture of before. Let me see here. Right, okay, so you just find the middle point, cross into the middle, recursively using effectively, binary sort, which is log n, and then log n. You find the closest here, and the closest here. And from here, and then after that, you combine them. But what if it's in the middle? I don't know. Yeah, okay, this one is like, oh, you should not be listening to me doing this one, because this one's the one I'm like, oh, I had trouble with this one. I still kind of don't exactly get it. Like, okay, the done the easy way. Yeah, I get that, because, you know, it's simple. Divide and conquer, don't really understand it. It's like, you gotta separate it, like, into multiple parts, and assume, and just hope that it's the outliers. Like, what does that mean? Alright, let's get rid of that. Alright, get rid of that. Alright, Steam, please. Dragon Ball Sparking Zero. I'm getting really tired now. I've been streaming for like an hour and a half. I've been teaching for an hour and a half. I thought it was like an hour. Oh, oh, I guess the download took a lot longer than I thought. Like, I started, what, 30 minutes before... Around 30 minutes before it came out, before it dropped. And then when it dropped, I did it like 4 minutes late, started the download. Yeah, no, okay, the game's done. Game's done. Okay. The other part that would have been, I would have taught, which, you know, I'll quickly just, like, blast through them, and then we can play Sparking Zero. Woo-wee! I love me my Sparking Zero. I've been waiting several years for this type of game. Alright, let me just pull this out. Alright. Divide and conquer. Oh wait, I'm missing a section. Okay. So I've already explained before that doing matrix multiplication usually takes about n cubed times, because it's like, it's actually more than n cubed, because it's like, no, it's n cubed. Because that's n, n, n. No, n, n, n. It's n cubed. So from here, we go. So typically, to divide and conquer this, it would have to be divide matrices into size n over 2. N divided by 2. So what you do instead is, if it was like a 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, you actually split these into 4 sections. Okay? So each part would be a 4 cube, oh, there's supposed to be a 4 cube here. 4 cube, 4 cube, 4 cube. So 16. Yeah. What is that, like? Yeah, 4 by 4 makes a 16 cube, yeah. 1, 2, 3. Oh. 4, there we go. Yeah, that's why I was confused. So you'd split them into 4, like this, and then work through it like this. But, ironically, it doesn't work like that. Okay, let me actually check. Nah, that's fine. Okay, so it does a cross. Oh yeah. Unfortunately, this still runs at n cubed. But the point of, like, teaching this was the idea of, like, oh, if you think of it in other ways. Let me just... So the runtime of it is 8t, because it's like 1, 2, 3, 4, and the other one 1, 2, 3, 4. That's the 8 over 2, because we divided the cubes into as like almost like 2, plus c n over 2 to the power of 2 to the power of 2, because this 1, 2 from here, and using Master's theorem, it's n log 2 of 8, which is n cubed. So we end up in the same speed, but it also gives you the idea of, like, there's this guy named Strassen, okay? And what he did was he figured out how to... Oh, geez, oh, man, I messed up my things a lot. I guess when I was clicking on them, it just, like, moved a bunch of them around. I'm gonna have to reorganize it. Okay. So you can see how it's like, instead of c of 1 equals this, plus this, it's basically 2 different multiplications happening here. So instead, what he did was, it was like an addition times something else with an addition, where it reduced the amount of total thing total operations. Like, while it's a lot more complicated than I'm pulling it out. I'm like saying it as. Let me just. Paste. Alright. So from here, so instead of it being multiplication, it'd be like this. So instead of it, it takes one less operation, basically. Which, if you do, it's like, it's 7 instead of, 8. And with master theorems, you plug those in, because A is bigger than B of K. You get slightly less, which is the whole point of this class, is to teach you how to more efficiently go through this. And yeah, that's really it. It's like all of it. I mean, there is technically one more bit called convex hulls, which I don't know. It's supposed to be okay. It's like points on a plane. Yeah. Oh, whoops. I guess I'll just put another bit here. So it's like understanding like points on a plane, which I already couldn't figure out how to do points on a plane. So I don't know. And then you use this as like a way to like, hey, what part connects like this? That's what you're looking for. And then you can do it through other... Well, actually, no, it's supposed to be like... combining the shortest distance between like two of them, so it'd be like this and then this. Be this angle actually, but Oof. Now Sparking Zero has come out and I have the game. I'm going to end this stream and then immediately open up the next one. So we're gonna be ending this. I hope you guys learned something today. I mean, I technically got better at my thing because I did understand it just a tiny bit more, you know. I hope I do good on my test, but we'll be calling it. We're not calling it in for today. We'll be shutting this stream off and then playing Sparking Zero. So we'll be yeah, you know, yeah, that's really it. Like, it'll take a couple minutes for me to like, you know, start everything up, but I hope you guys will come back in like the couple minutes I'm gone. All right. Okay. Bye bye.